We've got one more podcast for Unit 12. This is Miss Gray, and we're looking at catalysts today. What is a catalyst? Basically, it's a substance that can speed up a reaction without actually being used up in the reaction. Enzymes are one example of a catalyst. It's a biological catalyst in the cells of your body. Here's an instance of an enzyme where the active site brings two things close together so that the reaction can occur. We call the place on the enzyme that brings molecules together the active site, and the thing that attaches to it is called the substrate. A homogeneous catalyst basically means a catalyst that's in the same phase as the reactants. So if you have reactants in their gas phase and your catalyst is a gas phase, then that's homogeneous catalysts. What do you suppose we'd call a catalyst that's in a different phase as the reactant? Yeah, different has this prefix hetero, so that would be called a heterogeneous catalyst. And we'll look more closely at those in just a few minutes. So catalysts work because they allow reactions to proceed by a different mechanism. So we get a new pathway for our energy to follow. And the new pathway has a lower activation energy. That's why the catalyst makes the reaction go faster. So this means, since the pathway is lower, more molecules will have this activation energy, and the rate can proceed at a faster rate. The interesting thing is, though, that it doesn't change the overall change in enthalpy. So your delta E is the same. Your final minus initial is still the same amount because we start at one place, we end at the other. Doesn't matter how we get there. Remember, energy is one of those state functions. So if we start here and go up a high mountain, or we start here and go up a tiny mountain, as long as we end at the same place, then our change in energy is going to be the same. So here's another graph. Wow, this is a way better graph than my little sketch, right? So without an enzyme here, we would have a higher activation energy, but that enzyme, acting as the catalyst, can provide a different pathway for the reaction to proceed, and the overall change in energy, you'll notice, is the same. So from this place to this place, we get the same energy drop as we did with the catalyzed reaction. That energy drop is exactly the same, but it's the peak that got lower. So let's look at a heterogeneous catalyst. Platinum is a solid metal, and platinum is often used as a catalyst for hydrocarbon reactions. Here's one way that can occur. Hydrogen bonds to the surface of the metal because it's attracted to those electrons that are flowing freely across that platinum surface. This allows the bonds between the two hydrogens to be broken. Then along comes our alkene. Remember, an alkene is a double bonded hydrocarbon. So where we've got this double bond, we've got this nice flat surface to sit along the platinum surface, and so now we've brought our alkene in close contact with the hydrogen atoms. So the double bond breaks, and that alkene bonds to the catalyst. That allows the hydrogen atoms to bond to the carbon. We change our alkene into an alkane. So we've now hydrated this compound, or hydrogenated our alkene, and that's what they do like with fats and things. When it says hydrogenated or saturated fat, then they've extended the shelf life of that oil or that fat by putting all the hydrogens that can fit onto that molecule. And of course, that's the kind of fat that's not good for you, the saturated fat. Okay, now let's look at a homogeneous catalyst, one that's in the same phase as the reactants. One instance is when chlorofluorocarbons catalyze the decomposition of ozone. Here's what happens. The UV radiation from the sunlight strikes a chlorofluorocarbon molecule, and it causes a chlorine atom to break away from the molecule. This chlorine atom is then free to collide and steal electrons from somewhere else. Once it finds an ozone molecule, then it can steal the oxygen atom to form the chlorine monoxide and leave a molecule of ordinary oxygen, O2. Then, when a free atom of oxygen collides with that chlorine monoxide, then we have our regular oxygen form, and then that chlorine is free to go off and knock into something else, and perhaps that something else will be another molecule of ozone. In the ozone layer, where the ozone is shielding us from the UV radiation, then that's when a CFC becomes dangerous, because once it's up there, it can go on and continue to destroy one molecule after the next in the ozone layer, because that chlorine is not used up in the reaction. It's used in one step, then reformed in the next, so that it can go on and keep catalyzing further processes. Another example is enzymes regulating body processes. These protein catalysts are in the same phase as the other reactants. So an example is in the protein dystrophin. This is a muscle membrane protein, and for the body to be able to make the muscles work properly, we've got to have this enzyme functioning in its right way. If you're missing this particular section of this protein, then notice how the shape gets distorted. Right here is the shape that it's supposed to have. This particular enzyme is missing a piece of that enzyme, and so it distorts the shape, so that can no longer function, and this results in a condition known as muscular dystrophy. And so in the field of biotechnology, they're working hard to come up with enzyme therapies so that we know where the damaged enzyme is. We try to repair that or help the patient to get the proper enzyme into their body and into their body cells, so that their genetic disorders that they were born with can at least be treated and they can have some quality of life. Now let's look at the effect of the catalyst on the rate of reaction. Catalysts will speed up a reaction, but only to a certain point, because once you get past a certain level, adding more reactants won't change the rate, because the catalyst is considered to be zero order in the rate law. The catalyst doesn't really count. So you use up all of your active sites on the catalyst, and you're going to level out your speed. So the rate law doesn't depend on how much catalyst, but once you use up all your catalytic sites, you're not going to be able to speed up the reaction anymore. So the rate increases until the active sites of the catalyst are all filled up. Then the rate is independent of the concentration of your catalyst. Here's an example of an AP question involving catalysts. We have two reactions represented above. The first reaction is A plus B, and the second is X plus Y, or X2 and Y2, right? The potential energy diagram for reaction 1 is shown below. The potential energy of the reactants in reaction 2 is also indicated on the reaction. So see where it's starting off about the same level as reaction 1. Reaction 2 is endothermic, and the activation energy of reaction 1 is greater than that of reaction 2. So now that's the information for this problem. What's the question that they want us to answer? So for part A, it asks us to complete the potential energy diagram for reaction 2 on the graph. So let's get something to draw with. Here's my X and Y, so we'll start out at our initial. Is that you? No. We'll start out at our initial potential energy, and since it says that reaction 2 is endothermic, then we're going to have to end up at a higher energy. Doesn't matter how high you go, but let's just mark a spot that's higher than what we started with. It also tells us, too, that the activation energy of reaction 1 is greater than that of reaction 2. So when we draw this in, we can't go up as high. We have to go up high enough, though, that we're higher than the ending. So now I've drawn an endothermic reaction because I started lower energy than what I ended up. And my activation energy is less than that of reaction 1. And so that's how I can answer part A, sketched in the potential energy diagram. Let's look at part B. For reaction 1, predict how each of the following is affected as the temperature is increased by 20 degrees Celsius. Explain the basis for each prediction. So let's use the collision theory, okay? Because that's how we explain what happens with the rates of reaction. So, for reaction 1, explain how the rate of reaction is affected as the temperature increases. So, for reaction 1, since it's exothermic, and every time that we have a reaction, we know that temperature increases leads to rate increases, right? Because, this part's important. Let's explain this. Because the higher temperature means the particles are moving faster, and we get more collisions. Not only do we get more collisions, but the collisions we do get have more energy. More collisions with more energy. And that makes the rate increase, because more collisions with more energy means a greater chance of having particles with enough energy to overcome the activation energy barrier. All right, then let's look at the next part of the question. How did the increase in temperature affect the heat of the reaction? Okay, by heat of reaction, remember we mean delta H, the enthalpy, right? How is delta H affected by an increase in temperature? Let's look at our reaction. To go from the reactants to the products, we had an overall drop in energy. That's our delta H. So our enthalpy change is negative. This is exothermic. Does that change if I heat it up or if I go faster? No. Ultimately, when we start here and end here, it doesn't matter how fast you get over this curve, you're still going to start and end in the same place. So temperature has no effect. So increasing temperature has no effect on delta H. Because it's a state function. We may get there faster, but we still end up with the same overall change. So that's it for our podcast about catalysts. We'll work on more problems like these in class, so I'll see you there.